Hi, good day. I'm SIVAASHINI. Today I will be presenting our project on second order linear differential equation with constant coefficients. These are my group members. Now let us begin with the introduction part. A differential equation is a mathematical equation that involves an unknown function and its derivatives. It is used to describe how quantities change with respect to one another and plays an important role in mathematics, science, and engineering. Differential equations are widely used in real-world applications such as mechanical vibration, electrical, heat transfer, and control system. So in this project, we will focus on second order linear differential equations with constant coefficients, and we will explore different methods used to solve them, including the Laplace transform method.
Assalamualaikum and a very good day everyone. So I'm going to explain about homogeneous differential equation. So basically it is a second order differential equation that has this type of equation, and for the right side it has to be 0. That's why it is called homogeneous. So how do we determine if the equation is homogeneous? We look at the right side of the equation. For example, from the left example is it is homogeneous. Why? Because the right hand side has the value of 0. Meanwhile, the right equation is not homogeneous because the right hand side has the value of x. So it is very simple to determine whether the equation is homogeneous or not. So for methods of solving for homogeneous differential equation, for the first part is we have to change our equation. Let's say like equation from the number 1, we change to the characteristic equation like in the slide. And after that, we can find the roots by putting our equation in the calculator. And let's say we got the two different type of roots, such as let's say like m1 value is 3 and m2 value is 2. So we can use case 1 for the next step of our calculation. And for the case 2, if we got real but equal roots such that m1 and m2 has the same value. And for case 3, we use the case 3 when we have the complex number in our roots. And after that, we can find a general solution by looking back at our case 1, case 2, or case 3 approach, and we can use the general solution according to our roots, just like I said before. And for the number 4, if given initial or boundary conditions, we can substitute into the solution so that we can obtain values a and b. So let's dive into the example of homogeneous differential equation for better understanding. So first, we have this equation, and after that, we have to convert this equation into the characteristic equation. So we got r squared minus 3r plus 2 equals to 0. And then we have to factor or use quadratic formula from the characteristic equation. And this part, we can just include the value into our calculator. And after that, we can find the roots. So for this equation, we got root 1 is a 1 and root 2 has the value of 2. And since we have two real and different roots, we can use case 1 approach. So for the case 1 approach, we have the general solution of yx equals to c1 exponent to the power of root 1x plus c2 exponent to the power of root 2x. So we can just substitute the roots into the equation. So for the first root, we have 1. So we just include into the general solution. So we just got our equation. So that's all from me.
Non-homogeneous different equation. This is the step-by-step to solve non-homogeneous different equation. First of all, we need to find yc by make the fx is equal to 0. Next is a characteristic equation. Next we find the roots, and then we determine the roots type. There are 3 roots type. That is distinct, equals, and complex. After that, we find the yp by determining the particular integral type. There are 3, I'm focused 3. That is polynomials, exponentials, and trigonometric. After that, we need to add x the power of r, then compare to yc with r. First r we use 0. If the compares is have the same, we need to change it to 1, and if next also have the same, we change it to 2, and so on. Next, we differentiate it and substitute and equate. After that, we got the yc and yp. We using the formula and combine the yc plus yp that we obtain and get the y. So this is how we determine the yc and yp. For the yc root types, there are 3. There is distinct real roots, equal roots, and complex roots. And for yp, we have 4: polynomial, exponential, trigonometric, and product. So this is the example for non-homogeneous different equation. The example given is d square y per dx square plus 4y is equal to 5 sin 3x. First of all, we need to find the type of roots we use. If we're looking at this question, we know this is a complex root. So we use yc is equal to e alpha x c1 cos beta x plus c2 sin beta x. Then we proceed to particular, that is yp, and we're using the xr. Yp is equal to xr a sin beta x plus b cos beta x. It is because we know that is in the trigonometry. After that, we got yp is equal to a sin 3x plus b cos 3x. Then we compare it to the first yc we got. That is c1 cos 2x plus c2 sin 2x. So after check the corresponding terms in yc, we proceed due to no corresponding terms in yc. After that, we will differentiate the original yp, that is yp is equal to a sin 3x plus b cos 3x. Then we got the yp prime and yp double prime. And after that, based on the question we do is actually yp double prime plus 4yp is equal to 5 sin 3x. Then we use the yp that have we differentiate that we got and insert it into the initial question, and we got negative 9a plus 4a sin 3x plus negative 9b plus 4b cos 3x is equal to 5 sin 3x. Then we got a is equal to negative 1 and b is equal to 0. Next, after that, we insert the value of a and b into the equation. We do yp into the yp equation. After that, we use the formula that is y is equal to yc plus yp. We inserted all yc and yp we obtained, and that is the final answer, which y is equal to c1 cos 2x plus c2 sin 2x minus sin 3x.
Okay, Assalamualaikum and good day everyone. In this section, I will explain two important properties of the Laplace transform, namely the linearity property and the first shift theorem. Laplace transform is a mathematical technique used to convert differential equations in the time domain into algebraic equation in the Laplace domain. This method is widely used in engineering fields such as electrical engineering, mechanical engineering, and control system because it simplifies complex calculation. In this presentation, I will discuss how these two properties help us solve differential equations more efficiently. Okay, so we begin with the linearity property. The linearity property states that the Laplace transform of a linear combination of a function is equal to the same linear combination of their individual Laplace transform. In simple terms, instead of solving a complicated function all at once, we can separate it into smaller parts and transform each part individually. For example, consider the function 3t plus 2 sine t. Using the linearity property, we can write the Laplace transform of 3t plus 2 sine t equals 3 times the Laplace transform of t plus 2 times the Laplace transform of sine t. So, okay, after substituting the no Laplace transform formula, we obtain 3 over s squared plus 2 over s squared plus 1. This property makes calculation easier and help us solve differential equations in a more systematic way. Okay, so now we move on to the second one, that is first shift theorem. This theorem is applied when a function is multiplied by an exponential term such as e to the power of at. According to the theorem, if the Laplace transform of a function ft is fs, then the Laplace transform to the e to the power of f multiplied by ft can be obtained by replacing s with s minus a. Instead of performing lengthy calculation or integration, we can directly apply this theorem to obtain the answer. Therefore, the first shift theorem saves time and simplifies problems involving exponential functions. Okay, so we move on. Now let's look at an example. Find the Laplace transform of e to the power of 2t multiplied by sine t. First, we identify the basic function, which is sine t. From the Laplace transform table, we know that the Laplace transform of sine t is 1 over s squared plus 1. Using the first shift theorem, we replace s with s minus 2. Therefore, the result becomes 1 over open bracket s minus 2 close bracket square plus 1. This example shows how the first shift theorem allows us to obtain the solution quickly without carrying out complicated integration. Okay, so to conclude, we have discussed two important properties of the Laplace transform. First, the linearity property, which allows complex functions to be broken into simpler components before applying the Laplace transform. Second, the first shift theorem, which is used when a function is multiplied by an exponential term and enables us to shift from fs to fs minus a. These properties are important tools for solving differential equation and are widely used in many engineering applications. Okay, so that's all from me. Thank you for your attention.
Assalamualaikum and good day everyone. My name is FITRIYAH binti AZAMMANAN. My matrix number is CN250169. Today, I will explain a method for solving differential equations known as multiplication with t to the power n. The main idea is to recognize a hidden product rule inside a differential equation so that we can solve it more easily. By the end of these presentations, you should be able to identify the hidden derivative form, rewrite the equations, and solve it using integration. Before solving, we must recall the product rule. If u and v are functions, then d over dt of u times v equal u times d v over dt plus v times du over dt. For this case, let u equal t and v equal y. So we get d over dt of ty equals t times dy over dt plus y. This is the most important formula in this topic. Sometimes we see an equation like t times dy over dt plus y equal t. At first, it looks complicated because it has a derivative term, ay terms and at multiplier. But if we compare carefully, we'll notice some things important. T times dy over dt plus y is actually the same as d over dt of ty. So, instead of solving a messy equations, we rewrite it into a single derivative. Let me solve it. T times dy over dt plus y equal t. Focus on the left side. T times dy over dt plus y. We compare it with the product rule. D over dt of ty equal t times dy over dt plus y. They match exactly, so we rewrite the equations as d over dt of ty equals t. So, instead of solving a messy equations, we rewrite it into a single derivative. Let me solve it. T times dy over dt plus y equal t. Focus on the left side. T times dy over dt plus y. We compare it with the product rule. D over dt of ty equal t times dy over dt plus y. They match exactly, so we rewrite the equations as d over dt of ty equals t. Now, divide everything by t. Y equals open bracket t square over 2 plus c close bracket divide by t. Split the fractions. Y equal t square over 2t plus c over t. Simplify. Y equals t over 2 plus c over t. So, the final solution is y equal t over 2 plus c over t. General, t to the power n times dy over dt plus n t to the power n minus 1 times y is the same as d over dt of t to the power n times y. This comes from the power rule where d over dt of t to the power n equal n t to the power n minus 1. Memorize this pattern. T times dy over dt plus y equal d over dt of ty. T squared times dy over dt plus 2ty equals d over dt of t squared y. T cubed times dy over dt plus 3t squared y equals d over dt of t cubed y. Whenever you see this structure, think product rule immediately. So in the conclusion, this topic is not mainly about integrations. The most important skill is recognizing the hidden product rule. The steps are: first, identify the pattern. Second, rewrite as a single derivative. Third, integrate and solve. Once you master pattern recognitions, these equations become very easy. Thank you.
Now let us look at another example involving the multiplication by t property in Laplace transform. So the question is to find the Laplace transform of t sine 2t. First, we have to recognize that the function contains t multiplied by another function sine 2t. So this tells us to use the multiplication by t property, which states the multiplying by t in the time domain corresponds to differentiating the Laplace transform in the S domain. So the first step, we need to find the Laplace transform of sine 2t, which is 2 divided by s cubed plus 4. Next, we differentiate this expression with respect to s and apply the negative sign according to the property. After differentiation and simplification, we obtain the final answer where it is 4s divided by in bracket s cubed plus 4 cube. So this example demonstrates how Laplace transform properties can simplify calculations and make solving differential equations more systematic. In conclusion, in this ebook, we have learned that second order linear differential equations can be solved using different methods depending on the problem. The characteristic equation method and the Laplace transform method are among the most important techniques. Laplace transform is especially useful because it converts differential equations into algebraic equations, making them easier to solve. These methods are widely applied in engineering fields to analyze and predict the behavior of real-world systems. That's all from us. Thank you for your attention.